Hello, my name is Yeonseung Jung, and I oversee the high bandwidth memory DRAM lineup at the product planning team of SK hynix. I wish to take this time at GTC 2022 to introduce HBM3, our hallmark and latest HBM product. I will start with an overview of the HBM market, discuss HBM3's features and applications, and lastly, introduce SK hynix HBM3, which was successfully developed in 2021. HBM is specialized DRAM that first launched in 2015 with a focus on high bandwidth needed by AI machine learning or supercomputers. The market is still relatively new, and the main applications have been accelerators or high-performance computing so far. But I expect it to diversify into cloud data centers, driving assistance systems, and further into high-performance main memory for servers and other networking systems. More and increasing demand would come from other devices and systems that require high-speed DRAM as the 5G era unfolds. Overall, the HBM market size is set to grow exponentially at a 40% CAGR between 2020 and 2026, which is 3 times faster than DRAM market growth in the same period. On the right, you can see the trend of change between HBM generations. As of Q1 2022 present, HBM2E is the major product in volume production. SK hynix new HBM3 will become available late in the first half of this year and begin to gradually gain share then on. As the two most recent generations of HBM become market dominant with increasing supply of HBM3, the earlier HBM2 would be naturally squeezed out. But later on, a second generation HBM3 is expected by mid-2024. Followed by an HBM4 with an entirely new platform in the late 2026 or 2027. This slide first shows the trend in bandwidth, the most important performance factor for HBM. Bandwidth, indeed, is HBM's particular strength compared to other DRAM. The current mainstream HBM2E offers 460 GB per second of bandwidth, while SK hynix new HBM3 can achieve 819 GB per second. This represents a near 80% performance gain in less than 2 years. We expect the subsequent second generation HBM3 to deliver nearly 1 TB per second of throughput, while the HBM4 in 2026 may reach close to 1.5 TB to 1.8 TB per second. HBM specifications are evolving thus in line with industry needs, memory makers' technical capacity, performance requirements of processors that work in tandem, as well as the heat cooling capacity of end systems. As the market is also expanding rapidly, the outlook on HBM's trajectory continues to shift. We invite you to closely watch how fast this technology can advance going forward. The right side graph shows the trend in HBM package density, which is a product of individual die density and number of die stacks. HBM2 uses 8 gigabit die instead of 4 or 8 to make 4 GB and 8 GB packages. Current mainstream HBM2E uses twice larger 16 gigabit die for package densities of 8 GB and 16 GB. HBM3, set for mass production this year, will stack the same density chips in 8 or 12 die layers to offer 16 GB and 24 GB packages. The following second generation HBM3 will raise die density to 24 gigabit for an 8 GB increase in total density, and the next HBM4 will add another 8 GB to complete a linear upward trend. Now, for emerging HBM markets, HBM continues to diversify away from conventional AI inference and training applications. One market segment that HBM is sure to expand to in the next 2 to 3 years is autonomous driving. Levels 4 and 5 of complete autonomous driving, to be exact. At such level, a car must be capable of making and executing decisions without driver's interference based on changes in the surrounding environment and object perceived. This will require real-time processing of massive data collected through cameras and other numerous sensors. HBM's massive bandwidth will become necessary in this regard, driving full-blown market expansion from 2025 as level 4 to 5 ADAS systems take off. ADAS will require around 600 GB to 1 TB per second for DRAM bandwidth for level 3 systems, and nearly 1 TB to 1.5 TB for level 4 vehicles. Some models install the same hardware in main and sub-units for redundancy, requiring twice as much hardware per car. Importantly, reliability is a feature that differentiates automotive chips from commodity products. Unlike general-purpose servers or desktop computers in mostly stable, predictable environments, cars are exposed to long-time use in harsh environments, from the extreme cold of Arctic regions to scorching heat and humidity, which pose a direct risk to survival of the driver and passengers within. As such, it is imperative that cars ensure high levels of reliability and quality for protection against changes in surrounding temperature and environment. Furthermore, given that a single vehicle is required to keep using the same set of semiconductor chips fixed at production, automotive memory is expected to ensure 5 to 10 years of production support. Let me now explain HBM's position within the memory hierarchy. Memory semiconductors are segmented depending on their purpose according to the von Neumann structure to optimally support the central processor's computation. HBM is multifunctional DRAM that can serve both as a low-level L4 cache that handles large data near the processor, as well as main memory that sits farther away. Further down the hierarchy are commodity DRAM and CXL and SSD for data storage. All features considered, HBM is widely adopted in HPC and cloud systems, as well as high-performance graphic cards for compute support and advanced driver assistance systems. Press Worldwide reported on SK hynix's first HBM Memory on October 20, 2021. Our HBM3 was announced as the world's first and fastest DRAM available to date, with up to 6.4 gigabit per second in pin speed and 819 gigabyte per second of bandwidth in a 24 gigabyte package. The HBM3 represented an 80% bandwidth improvement in just 15 months since the previous HBM2E entered mass production in July 2020. We expect this newest product to be delivered to customers soon and contribute greatly to AI and HPC system performance. Let us now look at HBM3's architecture. HBM3 has 16 channels compared to 8 on the previous version. To give some background, HBM die shrinks do not directly translate into the expected speed improvement, as the higher density increase low access time, such as TRRD and TFO. For finer-grained data control, the channel count was increased from 8 to 16 smaller channels that allow multiple data locations in the DRAM to be accessed simultaneously. The downside here is that the added circuitry for segmenting and accessing the channels may increase the die size, while the multi-channel operation may draw more power for address control. This page shows cross-section images and major dimensions of HBM, including die thickness and size. While HBM3 comes in two different 8 and 12 die stacks. We will focus here on the 12 die option. To begin with, the HBM package is connected externally through a total of 7,775 I/O bumps. Package size is 11 by 11 millimeter, in line with industry consensus. While the package height is 28.3 meters or 720 micrometers. Inside the HBM and under C in the table, you can see a middle die height is indicated. This refers to the thickness of each die, excluding the top and bottommost when 12 dies are vertically stacked. While previous packages could only accommodate 8 of approximately 50 micron die, we have successfully ground the middle die to a 40% lower height of 30 micron on the HBM3, not to mention vertically stacking and connecting the thinner dies. To put it in perspective, a thickness of 30 micron amounts to only 30% of standard office letter, representing the cutting edge of existing semiconductor technology. In the cross-section scan on the right of 12 die stack HBM3, you can see that the core die thickness, gaps between each die, and TSV connects are very evenly distributed and aligned. In the image below of the sample bumps for 8 and 12 die HBM3, the bump is shown bonded in proper form without any pressurized areas on the solder or any non-wet. For example, improperly soldered regions. Here is the POD for HBM3. The top and bottom views show the package floor plan and the key dimensions. In the bottom view, the pie is rotated to the right. The A1 index mark position on the top left corner can be used as a point of reference. HBM3's largest feature difference with HBM2E is the existence of on-die ACC, or error correcting code. Each sub-word line in a bank that consists of 2 data buses with a burst length of 8 are treated as symbols. Up to 16 bits of error correction is supported per symbol for defects or sensing margin related failures. For multi-symbol errors, which are uncorrectable, the information is output via the severity pin as uncorrected error so that the end user may check and handle the relevant corrupted data. HBM3 also incorporates change in the refresh rate. In previous HBM, once the DRAM exceeded 85 degrees C, the refresh rate increased to retain data inside the capacitors. For such, the refresh interval decreased by 50% once the temperature hit 85 degrees C, and by another half past the 95 degrees C threshold. With HBM3, the frequency policy changed. Considering the performance trade-off during DRAM refresh operations, we relaxed the faster refresh threshold to ensure performance in customer systems. That is, the accelerated refresh is not triggered until the device reaches 95 degrees C, only after which refresh interval is halved. Until that point, the refresh frequency stays unchanged even after 85 degrees C. Now, about HBM's internal temperature sensing feature. Since HBM temperature is a parameter that can directly affect performance, SK hynix HBM employs a mechanism to provide real-time temperature data to the user. Using a 7-bit analog to digital converter, the HBM can output temperatures from 0 to 127 degrees C in 1 degree Celsius increments, which can be checked via the IEEE 1500. In addition, the temperature data for refresh operation is separately output as a 2-bit code, shown in the previous slide, and sent externally through the PI. Temperature sensors embedded in each die are mapped out in the left side schematic. HBM3's high bandwidth also stems from its unique device characteristics. For the transistor, crucial component in memory speed, HBM3 employs a metal gate with a new type of material to achieve 23% faster speed. In addition, the intermetallic dielectric, or IMD layer, was deposited with a lower K material, reducing the RC delay and signal coupling for speed gains and less power draw. All in all, HBM3 achieves a 10% lower plus alpha capacitance, which is instrumental to the overall performance gain. Now, for the ever more important, the thermal dissipation capability. Especially for HBM, controlling heat emission is both more crucial and challenging than for other DRAM, requiring the multiple variables be considered in order to develop an optimized product in this regard. Within the HBM, 8 to 12 of individual die are stacked on the top of each other, and the gaps between each die are filled with underfill, a relatively less heat conductive material, in order to create a structure that is capable of handling basic heat stress if the heat generated from the package bottom cannot be released quickly. The device temperature will continue to rise, which can rapidly degrade the chip's performance above a certain threshold. This is why a robust cooling mechanism is essential for HBM, and also why SK hynix has focused on developing an HBM structure with greater heat dissipation characteristics. Although we have already demonstrated the effectiveness of this mechanism on HBM2E, we have achieved ever greater gains on HBM3. In a simulation using a package with a HBM2E's size and structure combined with HBM3's power characteristics, we tested how each change on HBM3 contributes to temperature against the maximum die temperature being 100%. The top heat sink was assumed to be 88 degrees C in a real-world operating environment. First, adding the maximum possible number of the thermal bombs allows the HBM to release heat faster as highly conductive metals came to take a larger share of the structure instead of the underfill. Also, the need for less underfill due to the smaller gaps between each die reduced the overall thermal capacity and helped release instead of capture heat. Furthermore, the 10% larger die size on HBM3 allowed the heat to move faster to the topmost die. Altogether, the thermal interpretation showed that HBM3 can operate at a 25% lower temperature compared to the HBM2E in the same environment. We have thus explored the performance and feature characteristics of HBM3. I am so confident that SK hynix HBM3 will be instrumental in meeting extreme data processing needs of the world's AI machine learning, and HPC environments. With world-leading technology, SK hynix will continue to drive performance gains for next-generation HBM. Thank you for your attentive listening.